My name is Conrad Prisby. I'm a master's student at Embry-Riddle, Aeronautical University, and today I'll be presenting blind source separation for joint communication and sensing in IBFD MIMO systems. This paper is done by Dr. Sal Lee, Dr. Thomas Yang, and then myself, Conrad Prisby. So, talking about our motivations towards 6G communication, as you know, mobile data traffic is rapidly growing due to the increase in automation and devices that connect to wireless systems. So because of this, there's a shift towards millimeter wave for a higher bandwidth. And also, with this increase in devices, the spectrum scarcity limits capacity, which can increase cost. And because of these challenges, in-band full duplex allows us to transmit and receive data within the same frequency band. And this can improve the spectrum use without the additional bandwidth. And then this picture here just shows our ideal situation for IBFD, but unfortunately there is no ideal situation. So some of the challenges you'll come across is the self-interference, which is when the transmitted signal actually couples with the receiver chain. And then you also have multipath, which is just reflections off of environment. And then your standard noise. So, why blind source separation? We're going to use blind source separation, more specifically independent component analysis, to separate the mixed signals based on statistical independence. This is just by maximizing non-Gaussianity through fixed point iteration. And that self-interference challenge we're actually going to use for sensing. And we're going to use a signal of interest for communication. And this can prove to be cost efficient since it'll utilize present hardware for communication and sensing. So some past work, including these topics, blind source separation architecture has been developed for IBFD to improve computational efficiency. Also, existing approaches to sensing often rely on deterministic reference signals, while communication employs random modulation schemes. So basically, it's just saying like the sensing needs already known signal, and then the communication is random, so that kind of becomes difficult to combine. And then the blind source separation scheme has been proposed to mitigate aliasing for joint communication and radar scenarios. So this is where we come into our contribution. As I said before, we've seen blind source separation with IBFD, and we've also seen blind source separation with JCAS and vice versa. So we propose the application of all three together. So we're going to use the fast independent component analysis for JCAS, MIMO, IBFD deployment. And it's going to enable us to actually use the self-interference cancellation and environmental sensing simultaneously. So we're going to utilize our knowledge of the self-interference signal. And this validated the proposed framework through simulation under practical conditions in MATLAB. And as you'll see later, that the results do demonstrate that this can be effective for joint communication and sensing. So looking over at our system model here, we're going to simulate two nodes with the n amount of transmit antennas and an n amount of receiver antennas. And the transmit signal is going to be composed of our signal of interest, our direct, and then our reflected. And then our self-interference also are direct and reflected. We're going to be focusing more on node 1, which is just going to receive the mixed signal, including noise as well. And that's where the actual ICA algorithm will be applied. So continuing more into the system model, we're going to focus more on equation 3 here, which is just the canonical blind source separation form. Equation 1 and 2 are the same thing. It's just this one's in the matrix format. And I say k here at time k. This isn't time varying, so we're just going to set k to 1 just for convenience. And the R is going to be our received signal. The source self-interference, this is going to be known because that's coming directly from that transmit of that node. And then our H is going to represent our mixing matrix. And then our SSOI, our source signal of interest, is going to be completely unknown, which is this is what we're going to be looking for. And then our n is going to be our noise. And so going more into the mixing matrix here on equation 4, since we are utilizing our knowledge of that self-interference, we can assume the top row is going to be known, so we can just set that to the identity matrix. And since there's no interaction between the signal of interest with that self-interference, we will just set that to 0. And then the bottom row is where we're going to have our unknowns, which is going to be our self-interference. We still know it, but there's still going to be some reflections and minor noise that go along with that. And then, of course, our signal of interest is just going to be completely unknown. So going to our simulation setup, we, as I said before, it's going to be 2 nodes, each equipped with transmitter and receiver antennas. The HSI-R is going to be modeled as a Rician channel just to simulate a dominant lamp site with scattering and reflections. And then our HSI-C is going to be generated as a deterministic all-ones matrix with a small Gaussian noise to simulate coupling. And then, as you see, the self-interference is going to have both the reflection and the couple, but our signal of interest is just generated as 1 because as a Rayleigh distributed as 1 just because we don't, that's totally unknown. So there's no reason to split it up into 2 different values. And then our source self-interference and our source signal of interest are going to be BPSK modulated from -1 to 1. And then our source is going to be a combination of that self-interference and that signal of interest for a 4 by n, which n is just going to be our frame size. And it's 4 because it's 2 by 2. So for our simulation setup, n is going to vary from 50 to 500 in increments of 50, just to study the performance under different processing lengths. Each frame size consists of an average of 1,000 iterations at that increment, just to reduce the outliers. And then there's going to be 3 noise variance metrics with corresponding signal-to-noise ratios, starting with 20 decibels, 15 decibels, and 10 decibels, just to see how this system responds under different noise metrics, or noise values. And then for our evaluation metrics, we're going to look at the ergodic linear minimum mean squared error, or mean squared error. This is just going to be our average estimation between the actual mixing matrix and the estimated mixing matrix. And since it's a simulation, we can do this mean squared error test. And then we're also going to look at the signal to residual error ratio, which is just going to be our communication performance. And so what we're looking here is we want to see a higher signal to residual error ratio, and we also want to see a lower mean squared error. So looking at the simulation results here for our self-interference, you can see that obviously we're getting that downward trend that we want to see, but as the noise increases, it starts to struggle a little bit, and that's to be expected. Likewise with the signal of interest, it's a similar pattern where that higher noise is going to struggle a little bit more. This signal of interest isn't going to have as good of a performance as that self-interference because that signal is a lot harder to extract than just that self-interference. And then looking at our SRER, like I was saying, we want to see an upwards trend on this, but our higher noise kind of plateaus here, which means they kind of struggle to extract the actual signal from the noise. And then our iterations converge. As you can see, the higher frame size, the better the performance, but then there's still the occasional outliers, and it still struggles with just that higher noise. So in conclusion, we proposed a blind source separation based framework to enable JCAS in IBFD MIMO system. We leveraged the known self-interference signal and repurposed self-interference signal for environmental sensing. We applied the fast ICA algorithm to separate the self-interference signal from the signal of interest, and then based on the results, we can confirm that the proposed method is capable of JCAS. obviously the environment was very controlled, and the system performance increased with the frame size. So for future work, we'd like to investigate a suitable blind source separation algorithm for time varying channels. Is because the fast ICA algorithm is only good with a fixed mixing matrix. So if there's another algorithm we could find that actually can adapt with the changing mixing matrix, that would have better results for time variation. I'd also like to integrate machine learning with dilated convolution just to capture patterns and add prediction accuracy. And then develop a reinforced learning-based strategy to adjust frame sizes based on real-time channel variation estimates. We also did a paper with the time variant. The QR code here is a link to that paper as well. And thank you. Any questions?
We have time for questions. Anybody with questions? Can you said so this did not have time varying,
No,
but
it
you did some work.
Yeah.
Can you just kind of talk to the results? I mean, are they what happened?
So this was the setup for the time variation simulation. It just is going to increase linearly. And then, like I said, since the fast ICA only works with a static mixing matrix, we just took the midpoint of the channel size of that mixing matrix, and we used that for the ICA algorithm. And the results.
So you still use the same algorithm?
Yeah, it's the exact same algorithm. It's just we use that midpoint because it has to be fixed.
Okay.
And the performance is shown here. After around 200 to 250 frame size, it's going to start to degrade, which is to be expected because we're using a fixed mixing matrix. And likewise, obviously the time variation speed at 0 is just the last paper, right? So that was just kind of our baseline.
And is that what, when you're talking about time variations, that's the channel that's only variable, not the transmitter receiver? Those are fixed still in this case as well.
Yeah.
But the base stations, I guess, are fixed. Okay. That's interesting. What do you have an estimate or a feel for computational complexity of that algorithm? Computationally, you have measured that. That would be interesting to see.
Yeah. Actually, that would.
That's great. It's good work. Thanks.